In this video, we will see how to evaluate an object detection algorithm. Imagine that we have an annotated validation set, which is shown in green here, and we also have bounding boxes predicted by our object detector, which is shown in red. We should check how well our predicted bounding boxes match the ground truth annotation. To discuss the metrics, let's first look into the basic blocks needed to compute them. Let's first understand the concept of intersection over union, which is usually called IOU. It evaluates the overlap between two bounding boxes. It requires a ground truth bounding box and a predicted bounding box. IOU is computed as the ratio of the area of their overlap to the area of their union. So that is why it is said intersection, which is the overlap, over, which is divided by union. To evaluate detections, we need to set an IOU threshold. For example, we could set a threshold of 0.5. If the IOU is higher than this threshold, we'll consider that the prediction intersects well with the ground truth. Next, we need another metric called the confidence score. Confidence score is the probability that a bounding box contains an object. It is usually predicted by the classifier. It is the output of the classifier. For example, in this slide, the green box shows the ground truth. The orange box shows a good overlap, but the confidence is low. This could be because the classifier thinks that the object inside the bounding box is a different object. The blue box shows a bounding box with reasonable overlap and also high confidence. We need to set a confidence threshold, for example, 0.5. Now, this threshold is completely different from the IOU threshold. So we are talking about two different thresholds here. One is the confidence threshold, which says how confident we are that a particular object or a particular class is inside a bounding box. And the second one is the IOU threshold, which tells us how well the localization has worked. So one you can think about as the localization threshold, which is IOU threshold, and the other one is the classification threshold, which is the confidence score. Now let's combine the confidence score and the IOU values to evaluate the detections. A detection is considered a true positive only if it satisfies these conditions. First of all, the confidence score should be greater than the confidence threshold, which tells us that we have found the object we were looking for. Not only that, we also need a good overlap. So the predicted bounding box should have an IOU greater than the IOU threshold with the ground truth bounding box. So those are the two conditions that it needs to be satisfied. What we are saying is that not only is the object detected, it is detected at the right place. If we detect an object with high confidence, but it is actually not present, we call it a false positive. We may also get a false positive when the object was detected with high confidence, but it was not localized well, and therefore the IOU was below the threshold. False negatives are cases where there was an object present, but we missed it completely. We also get false negatives when the object is detected, but with low confidence. Because of this, we have to filter out this bounding box, and the result is a false negative. Now let's look at recall and precision. We have discussed this in classification lectures, but let's just go over it once again. Recall is the ability of a model to find all relevant objects, meaning all the ground truth bounding boxes. It is the percentage of true positives detected among all relevant ground truths. Precision, on the other hand, is the ability of a model to identify only the relevant objects. It is the percentage of correct positive predictions. Once we have an object detection model, we can use it to create a precision recall curve by thresholding the confidence. Using various confidence thresholds, we can get pairs of precision and recall over the entire validation set. And we can plot these values to get the precision recall curve. When the confidence threshold decreases, recall increases monotonically and precision can go up and down, but it usually decreases. Now let's look at a concept of average precision. The recall precision curve itself can be used as a performance metric for object detection algorithms, but it's hard to compare two different detectors using the recall precision curve. We want a metric that is a single numeric value and not a curve. The metric most commonly used in object detection is called average precision, or AP. It is essentially the area under the recall precision curve. The higher the average precision, the better is the model. There are several variations of average precision. In fact, typically, every repo has its own implementation, which is subtly different from other implementations. Because of that, AP values in different repositories and benchmarks are not totally comparable. For example, to make the metric more robust, typically algorithms use an interpolated version of the recall precision curve. In this case, we do not measure the recall precision pairs for every possible confidence threshold. Instead, we select some points, measure the recall and precision in them, and then interpolate all the values in between. For example, in Pascal VOC dataset, the average precision is calculated by interpolating 11 equally spaced points. And you can look at the formula for average precision here, and it shows how it is computed. And in this slide, P interp R means that interpolated precision value corresponding to the recall R. Average precision is defined for single object detection, but it can also be generalized to multiple class object detection. The metric for multiple class object detection is called mean average precision, and it is defined as the mean of average precision across all classes. So this is slightly confusing because mean and average kind of mean the same thing, but the first mean corresponds to an average over classes, and the second one, when we say average precision, it is the average precision over the class. And this is usually called MAP. The MAP used in COCO Object Detection Challenge also considers the mean average precision at different IOU thresholds. This metric is better at representing various localization errors. Average precision is widely used to evaluate object detection algorithms, but it is rather unintuitive metric. Let's manually compute the AP values to better understand it. Let's assume there are two images with 5 ground truth objects represented by the green bounding boxes and 7 detected objects represented by the red bounding boxes. Each detected object has its confidence level and is identified by a letter A, B, C, D, E, F, and G. Now, the following table shows the bounding boxes with their corresponding confidences. Let's assume the IOU threshold is 30%. Based on that, we estimated whether the detection matches a ground truth box in the 4th column. Sometimes there are more than one detection overlapping a ground truth. For those cases, the detection with the highest IOU is considered as matching, and the others are considered not matching with the ground truth box. This rule is applied in the Pascal VOC 2012 metric. The precision recall curve is plotted by pairs, recall, precision, of the accumulated true positives and false positive detections. To do this, we should sort detections by their confidence scores, calculate recall and precision for each detection. Now, let's look at each detection in the sorted list, and going through it, every time accumulate the current number of correct and incorrect matches we meet. Detection C has a good ground truth match. We add 1 to the correct match accumulator and add nothing to the incorrect match accumulator. This means the current precision is 1. We know that there are 5 ground truth boxes in total, and we found only 1 by now. So the recall is 0.2. For detection E, there is no ground truth match. We add 0 to the correct match accumulator and 1 to the incorrect match accumulator and get a new precision value of 0.5. The recall stays the same as the match is not correct. Detection A has a good ground truth match, So the precision increases to 0.66 and the recall also increases to 0.4. Now, if we continue doing the same for every detection, we'll get a corresponding recall and precision pair for each of them. We are ready to plot the recall precision curve. By plotting the precision and recall values, we get the following precision recall curve. As we had mentioned before, there are two different ways to measure the interpolated average precision: 11-point interpolation and interpolating at all points. Let's compute both metrics. To make the 11-point interpolated average precision, we should average the precision at a set of 11 recall values, as shown here. By using the interpolation at all points, we can think about average precision as an area under the curve, or AUC, of the precision recall curve. Interpolation by 11 and all points provide a little bit different result. And when we use 11 points to interpolate versus all points, we see slightly different results. So you can go over these slides and try to do this calculation yourself and get an idea how this metric is calculated. That is all we wanted to cover in this video. Thank you.